This presentation will examine the two-sample z-test for proportions, problems in context, or word problems. When is it fair to use the two-sample z-test for proportions? Well, the two sets of data must come from simple random samples. The sets must be independent. There must be a large number of successes and a large number of failures in each set. The population must be significantly larger than the samples. So here's an example for us to look at. A random sample of 75 women enrolled in an intro stats course, and 20 of them earned a grade of A. A random sample of 82 men enrolled in an introductory stats course, and 18 earned an A. So these are samples that are supposed to reflect the entire population. This population is all women enrolled in an introductory stat course, maybe across the country. And this sample comes from a population of all men across the country in intro stats. And the question we ask is, can we conclude that there is a significant difference between the two groups? If we had all the men and all the women and looked at the proportion who earned A's in each, would there be a difference? Can we make that inference based on our sample? So here's our null hypothesis and alternate hypothesis. We're asking for a significant difference, so this is a two-tail test. P1 does not equal P2. So H0 subtracting P2 from both sides, we get P1 minus P2 is 0, and P1 minus P2 is not equal to 0. Proportion of women who earned A's, 20 out of 75. Proportion of men who earned A's, 18 out of 82. So there's our test statistic, but remember, P1 minus P2 on our H0 was 0, so we're going to just make this 0 and work with a simpler version of this test statistic. That's the form we like to use. So there's our H0 and HA. P1 hat 20 out of 75, P2 hat 18 out of 82. There is our test statistic. Getting P bar, 20 plus 18, 38 overall A's, 75 plus 82, 157 total people, for a P bar of 0.242. Q bar is 1 minus P bar, or 0.758. So now we have to plug all of those numbers into our test statistic formula, and we will allow ourselves to do that using Excel. So we have P1 hat, number of successes divided by the total, will be 20 out of 75. So we'll equal this number divided by 75. And then P2 hat will equal the number of successes in the second group divided by the total. Now to get P bar, we need the total number of successes divided by the total number of trials, equals total number of successes, first group, plus second group, divided by the total number of trials, first group, plus second group. So we get a P bar of 0.242, and Q bar, of course, is 1 minus P bar. And now to get our Z, we're going to have to use our somewhat complicated formula. P1 hat minus P2 hat divided by the square root of P bar Q bar over N1 plus P bar Q bar over N2 and we get 0.689, which is not a very extreme Z, so that indicates to us the direction this is likely going to go. So looking at this, we have a two-tailed test. 0.689 is here. I need the area to the right of 0.689. I need the area to the left of negative 0.689. CDF negative 0.689, normal 0, 1. We get 0.2454. So the area here is 0.2454. Similar, the area here will be 0.2454. And then our p-value is the sum of those two areas. Our p-value will be 0.49, which of course is a large p-value. So what that means is, assuming the men and the women came from populations with identical proportions, the chances of getting numbers this different just by random chance is 49%. Well, that's fairly likely, which means there's a chance H0 really was true. Since the p-value is large, we fail to reject H0. We do not have enough evidence to conclude that the overall proportions of men and women who earn A's are different. They may be the same. We do not know. Okay, one more example here. A random sample of 100 seniors found that 30 approved legislation that would permit gay marriage. A random sample of 200 college students found that 118 approved legislation that would permit gay marriage. Can you conclude that the overall proportion of seniors who approve is less than the overall proportion of college students who approve? So this will be a one-tailed test. We're saying the proportion of seniors is going to be less than the proportion of college students. Subtracting P2, we get this version. 30 out of 100 seniors, 118 out of 200 college students. There's our test statistic. Of course, P1 minus P2 will be 0 to make our computation somewhat simpler. So we want to go ahead and construct our test statistic. P bar, 30 plus 118, a total of 148. Approve of the legislation out of how many total? 100 plus 200 out of 300 total people in our group. So P bar is 0.4933. Q bar is 1 minus P bar, or 0.5067. So if we want to plug these in, P1 hat, 30 out of 100.3. P2 hat, 118 over 200 is 0.59. P bar, Q bar, 0.4933, 0.5067 over N1 over 100. P bar, Q bar, 4933, 5067 over N2 of 200. And we will solve this using Excel. So here we're going to have 30 over 100. Here we're going to have 118 over 200. And you'll notice the work is done for us. I programmed the spreadsheet on the last example, so it immediately comes back and gives me a Z value of negative 4.736. That is a very large Z. Remember, on the Z distribution, 99.7% of the data is within 3 standard deviations of the mean. This is negative 4.7 standard deviations. So 4.7 standard deviations below the mean. Very extreme value. So there's H0 and HA. There's our Z. This is a one-tailed test. So I put negative 4.736 here, but in fact it may even be further over. We're looking for how much area would be in that little itty-bitty part of the tail. We ask Minitab CDF negative 4.736, semicolon normal 01. And it basically gives me 4 zeros. 0000. So essentially, at least to 4 decimal places, there's nothing there. So if that's 0, that's going to be my p-value. So my p-value here is the very small number of 0.0000. Now what does that mean? That means assuming these were true, assuming the proportion of seniors and the proportion of college students were identical, if those proportions were identical, the probability of getting numbers this different just by random chance is less than 1 part in 10, 100,000, 10,000, less than 1 part in 100,000. So since that's so small, the reasonable thing to do would be to say, no, chances are that's not true, and now we do have evidence that those two populations would have proportions such that the proportion of seniors would be less than the proportion of college students. So how do we conclude that? Again, there's our H0 and HA, there's our p-value. Not exactly 0, but 0 to 4 decimal places. And we say since the p-value is small, our conclusion is to reject H0. And this time we have strong evidence to conclude that the overall proportions of seniors who support gay marriage is less than the overall proportion of college students who do. And that will complete this presentation.